first step to understanding how we're going to calculate these confidence intervals is to really see what they represent and how this table is associated with our confidence intervals. So, when it asks us to find the z-value you need to calculate large sample confidence intervals for the given confidence level, I'm going to walk you through the actual math of how we do it. Then at the end, I'm going to tell you the three common ones, which are really just the ones that you have to memorize or have in your notes and use for the future. But you should know how to do this process to see where they came from. So when I'm talking about a 99% confidence interval, what that really means is if I took the entire normal graph and I wanted the 99% of values that are closest to the mean, that would mean that this shaded area in the middle that the confidence interval is going to take into account contains 0.99 of the total probability under the normal curve. What's left over is this tail here and this tail here. Within those two tails is the total of alpha, or the chance of making a type 1 error. So alpha represents this unshaded portion. That means if 0.99 is in the shaded area, 1 minus 0.99 equals 0.01, which in this case is our alpha. It's what the total area needs to be in the unshaded regions. It's easier to read this table based on what's to the left of something. So instead of concentrating on both of these that are 0.01, I'm going to look at only this left-sided unshaded region. For that, I'm going to do 0.01 divided by 2, because there's two equal unshaded regions. That gives me 0.005, which is my alpha over 2. What we're really looking for in the formula is z alpha over 2. Or in other words, what z value has alpha over 2, or 0.005, to the left of it. So what I'm doing is I'm looking on the middle of my table for 0.0050. In my table, I go to the negative side, 0.005, looks like I'm in the row negative 2.5. As I read over that negative 2.5 row, I see that at negative 2.57 and negative 2.58 is where it switches. Negative 2.57 is 0.0051. Negative 2.58 is 0.0049. We're looking for the z-score that's got 0.0050 to its left. That would be right in between these two. So really, it would be a z-value of 2.575. You may be asking me, well wait, how come these are negative and you wrote it as a positive? Basically, this z-score would be negative 2.575 and this z-score would be positive 2.575. But when we get to doing the actual formula for calculating a confidence interval, in the end you end up adding or subtracting it from the mean you found. So the sign doesn't really matter, because in the formula it puts it in as plus or minus, it uses both versions. That said, we usually report it as the positive because we're just more used to seeing the positive numbers in the formula. So for a 99% confidence interval with 99% of the values in the middle and only 1% on the outside, the z-score where that happens is at a z-score of negative 2.575 and positive 2.575. That's why our z alpha over 2 is 2.575. For part B, they phrase it a little differently. They tell us that 1 minus alpha equals 0.95. Really, that's the exact same thing as a 95% confidence interval. So in this case, graphically, we would have 0.95 between two unknown z's. So the area under the curve would be 0.95 here. Since 1 minus alpha equals 0.95, I could rearrange this, take alpha to this side, subtract 0.95 from that side, and I'd find out alpha equals 0.05. That means the total of these two unshaded areas is 0.05. We only want one of the two. So we're going to take alpha and divide it by 2. 0.05 divided by 2 gives me 0.025. what that tells me is I'm looking for something that has 0.0250 area to its left. Again, I go back to my table. I go look for 0.0250. I see that it's happening in the negative 1.9 row. As I move over, there's an exact table entry for it. It happens at exactly negative 1.96 as a z. By the same idea, the one that's going to be on the right-hand side that's symmetric is positive 1.96. So in this case, my z alpha over 2 equals 1.96. It's possible that Cengage will ask you to do something like with a 98% confidence interval with alpha equals 0.03 or something else that's slightly different than these. But really in my class, anything I do in a test is going to be based on either 99%, 95%, or 90% confidence. So we know 99% confidence every time is 2.575. You do not need to do this math every time. We know that 95% confidence every time is 1.96. You do not need to do this math every time. And the one that we didn't do, 90% or 0.90, for that confidence, the z alpha over 2 is going to be 1.645. It's another one of these cases like 2.575 where it's right in between two of them, so we generally call it 1.645. As long as you have these three key numbers, 2.575 for 99%, 1.96 for 95%, and 1.645 for 90%, you have the three things that you need in order to start creating confidence intervals.